So hi everyone, thanks for joining us today and welcome to today's discovery session. These sessions are meant to support students, businesses, and other organizations with an understanding of how to use data and artificial intelligence. But before we get into it, I'd like to begin by acknowledging that DeepSense works out of Mi'kmaq, the ancestral and unceded territory of the Mi'kmaq people. This territory is covered by the treaties of peace and friendship, and we'd like to recognize the Indigenous peoples of all the lands that we're on today. We want to ask that everyone takes a moment to consider the territory in which they're situated and their own personal responsibility in processes of reconciliation. And for those of you who don't know me, my name's Alyssa, and I'm the communication specialist with DeepSense. And for those of you who don't know what DeepSense is, I'll give you a little introduction. DeepSense is a project based out of Dalhousie University in Halifax, Nova Scotia, but we work with universities and colleges across Atlantic Canada. We work with companies in the ocean sector who are interested in harnessing the potential of data and creating a smarter ocean economy. We connect these companies with the next generation of AI, machine learning, and data experts, aka you. We work with companies to create a project that best suits their needs, and then we find a researcher and a student to help execute the project as either a master's research project, a co-op, or an internship. We've had past projects in data analytics, data collection, data visualizations, data cleaning and processing, and of course, AI and machine learning. Projects could be anything from creating a deep learning model to track fish, or creating a prediction model for safe navigation in the Halifax Harbor, or even a computer model that can identify whale shapes from aerial images. And if you've ever wanted to grow your skills and work on real projects and gain industry experience, then make sure you submit your information to our student pool. Projects, internships, and co-ops pop up throughout the year, so it's useful to throw your name into the student pool because it's the first place that we'll check to find someone to fill a position. I will share a link to the pool in the chat after I finish talking, and then I'll make sure your resume is rocking because you want to stand out, since only those who are selected for an interview will be contacted. And so for today's session, we're going to explore what latent spaces are, how they power generative machine learning systems, and discuss many of their applications found in both research and industry. Latent spaces are the backbone of many generative technologies, so anyone with an interest in the inner workings of generative AI or machine learning in general should be attending. So I'm glad to see everyone here today, to see that you're interested in those kinds of things. And we're going to discuss how latent spaces can be used in the context of creative tasks, such as digital musical instruments, and then follow that up with a discussion of generative AI as it relates to potential DeepSense initiatives. And today's session is led by Matthew Peachey, a third-year PhD student who's researching at the intersection of human-computer interaction and machine learning. Matthew's current work currently focuses on exploring how generative systems can be used as highly creative tools that are both engaging and useful for end users. Matthew also has experience working in AR and VR, cybersecurity, and web development. If you have any questions throughout the presentation, we'll be taking them at the end, but feel free to drop them in the chat at any point, or you can use the question and answer box. And that is more than enough for me. Let's hear from Matthew.
Thanks for the kind introduction, Alyssa. I'm just going to go ahead and share my slides so that hopefully everyone can see them. We'll give it 1 second here. Perfect. So hopefully everyone can see those slides. Alyssa, do you mind letting me know once you're able to see them, and then I can get started?
We cannot see them yet.
All right, we'll give it 1 second because it should be sharing. So.
Yeah, I'm not sure.
All right, let's try now. How
Okay.
about it? Awesome.
Oh, there we go. Okay.
Perfect. Sorry about that. All righty. So once it loads up in full screen mode, I think we're good to go, and I'll start. Or you can still see them, Alyssa. I'm sorry, I just can't see the Zoom screen.
Yeah, no worries. You're in full screen.
All right, great. Wonderful. Well, hello, everyone. Thanks for having me here today to talk a little bit about latent spaces. And like I've titled this short talk, it's about what they are and why they matter. And so first, a little bit about me, although Alyssa covered most of it in the introduction. My name is Matthew Peachey. I grew up here in the Halifax area, so always been close to the ocean and always interested in these types of topics that DeepSense is working in. My involvement with computer science is I graduated with a Bachelor of Computer Science from Dalhousie in 2021. But currently, I'm now, like Alyssa mentioned, a PhD student researching at the intersection of human-computer interaction and machine learning. And then I've also participated in a couple of DeepSense's Ocean of Data challenges that they've put on often. And so had a wonderful experience working on some projects in that area. And so I'm glad to be back now chatting with some DeepSense folks. So really quickly, what we're going to talk about today. So I want to start with a super quick refresh on some basic machine learning concepts. I haven't geared this presentation to dive into any of the super detailed portions of ML and implementation, but rather just thinking about how the systems work from a higher level. After we've done that, we'll talk about what latent spaces are sort of generally, what we mean by latent space, how they work, some characteristics of latent spaces. And then importantly, we're going to think about why they matter. And in this case, that would be their application in generative ML or generative AI. And so specifically, we'll take a quick look at some architectures such as variational autoencoders or VAEs and generative adversarial networks as well. And so then, like Alyssa mentioned in the introduction, my research currently focuses primarily on how we can apply these technologies to digital musical instruments. And so I'll talk a little bit about that. And then, of course, I want to think about how we can apply this technology into perhaps some potential DeepSense applications in the ocean sector. And then, of course, we'll have time for questions and discussions. I'd love to hear your thoughts and engage in a good discussion about these topics. So here's our quick refresh on machine learning. And so anyone that's done sort of an intro to machine learning or has an interest in machine learning has likely heard of supervised machine learning. And this, what it works is it uses data to learn some kind of relationship between inputs and outputs. And so I've shown here two main types of tasks in machine learning. The first is classification, which is used to determine what type of thing something is or what class an input belongs to. And so this could be things like image detection, video detection, et cetera, really trying to put a type to your data. And then on the other side of things is regression, which is used to determine a numerical value based on input. And so you can sort of see based on your inputs what the most likely numerical value would be. And this can be continuous variables rather than classification we kind of think is discrete or categorical features. So what is a latent space? That's a great question. So two possible definitions that I've scripted right from some internet sources. The first from Wikipedia is that a latent space is an embedding of a set of items within a manifold in which items resembling each other are positioned closer to one another. So that's interesting. Another definition says that a latent space is an abstract, multi-dimensional space containing feature values that we don't necessarily interpret directly, but which encodes some meaningful internal representation of externally observed events. So that definition feels like a lot of jargon. So simply put, I like to think of a latent space as an organized representation of some compressed data. So what are some characteristics or some typical properties of a latent space? So typically a latent space, you'll want your dimensionality of your latent space, whether that be a two-dimensional plane, three-dimensional, or get into very high n-dimensional, which is where that manifold concept came from. You want that dimensionality to be smaller and usually significantly smaller than your feature dimensionality. And what I mean by feature dimensionality is all of the inputs coming from your input data and those features that you've derived. You want the dimensionality of your latent space to be smaller in order to sort of form some sort of bottleneck, and so that you're able to have dimensionality reduction. And then so moving on, taking from one of the earlier definitions, we want to observe that similar input data should be positioned near each other in the latent space. And so what that means is if we're thinking of, say, images of animals, if you have lots of dogs, you would expect that the way the latent space is organized is that all the dogs are together, whereas all the cats are perhaps close together, but in a separate section of your latent space. And so latent spaces, though, are typically not very interpretable by default. And so what I mean by this is that latent dimensions don't necessarily correspond to attributes of the output. Although there are strategies now in research for regularizing that space in order to make interpretability much higher. And so what I mean by this is, taking the cats and dogs example, it wouldn't be to say that one dimension of your latent space would necessarily smoothly transition from images of cats to images of dogs. But we'll talk a little bit more about interpolation here in a little bit. So unlike supervised machine learning, which was our classification or regression tasks, generative machine learning aims to learn an underlying representation of a data set and then use that representation to generate highly realistic, but also previously unseen samples or new data. And so where the latent space comes in is this underlying representation, which is usually related to statistical distributions of the data and sort of how that data is built. This is typically represented by what we call a latent space. And so sampling from that latent space is what is going to result in the generation of new data. And so, like I mentioned, for a perfectly trained model, this generated data should be indistinguishable from data points in your original data set. So if it was a very well-trained model, you would expect generated images of dogs to be very lifelike, very realistic. But of course, we acknowledge that it's rare for an ML system, especially in research, especially on the cutting edge, to be perfect. And so we oftentimes will observe some lossy effects, which you may have seen, like blurrier images that are being generated, or images that perhaps have non-lifelike features. So like I said, we'll talk quickly about two of the main latent space driven architectures. The first being a generative adversarial network, or a GAN. These are introduced about a decade ago now by Goodfellow. And so how this works is there's two main neural networks, which is a generator, G. And what the generator does is it takes from a latent space, or it samples from a latent space, and generates new data in the form factor of your real data. And then what the discriminator does is it compares real data to generated data, and it determines whether or not the input it's seeing is real, or if it's fake, or if it's generated. And so the way these are trained is you train the generator to get really good at generating images, while adversarially, meaning against each other, train the discriminator to be worse and worse at determining if it's real or if it's fake. That way, you achieve the indistinguishable part of generated content. So moving on, we'll talk about variational autoencoders as well. And so this again uses two neural networks, typically to run the VAE. You have an encoder neural network, which learns to encode your input data to a location within the latent space using these two properties, which is mean and standard deviation, sometimes variance as well. It really depends on your implementation. And then a decoder network, which learns to reconstruct the data from a latent vector back into the original form factor of your input data. And so the way that a VAE is trained is by comparing the loss between real data and reconstructed data. And so, of course, the real data is what you're feeding into your encoder, and then the reconstructed data is what's being outputted by your decoder. And so then the loss is just the difference, or the error between those two data points. So let's talk now a little bit about some interesting attributes about latent spaces. And so a typical task that was found while these architectures were being introduced was generating MNIST digits. And so anyone that's done image classification, basic CNN type of work will probably be familiar with MNIST digits. They're sort of the handwritten data set of digits. And so then what researchers were doing was, how can we use that data and then try to generate new digits? And so we see here from Penkovsky that when you use a two-dimensional latent space in your VAE, you can plot the different outputs and see and observe smooth transitions between your various digits. And so, for instance, you can see sort of in the top left quadrant of your latent space, there's a lot of different zeros. But then as you move to the right, you can see the zeros sort of smoothly transform to 8s and then to 9s and then to 7s. And you sort of observe this throughout the latent space. And so that's one big part about latent spaces, is that you want to be able to sort of fill in the gaps in order to generate that previously unseen data. So another interesting thing that researchers discovered while trying to find some methods for interpretability in latent spaces is that Radford et al. Showed that you can actually apply vector arithmetic within a latent space in order to generate some desirable properties with your outputs. And so in this case, they were showing how, again, using a very high dimensional space, in this case, a 100 dimensional latent space, you can still use vector arithmetic. And so, for instance, this example that they published shows how you can take samples of a smiling woman and then subtract the vector from the latent space of a neutral woman, add an image vector in the latent space of a neutral man, and then the result will be a smiling man. And so they have lots of other examples, but this just sort of shows and illustrates that you're able to perform some interesting arithmetic operations within your latent space and see some interesting results be outputted as well. So, quick summary, GANs and VAs are both quite popular generative ML architectures. They both use sort of a two neural network system, but in fundamentally different ways. But then, like I said, both also rely on the premise of a latent space in order to not actually generate new data. And so there's tons and tons of domain or task-specific variants of these architectures. And so depending on what you're actually trying to achieve, you might use a conditional GAN, which has an extra step to say, I want to generate images of a certain type. WGAN, MusicVey, RVey, these are all domain or task-specific variants of these generative architectures. Of course, there's other architectures out there now, big ones like transformers or GPT, diffusion or stable diffusion models. But we're going to sort of focus where my research has laid, which is on VAEs for the next segment of this session. So, like we mentioned in the intro, my work has primarily laid at digital musical instruments recently. And so one instrument is a synthesizer, which is an electronic musical instrument that's used to generate audio signals. There's tons and tons of different types of synthesizers. But one thing that a lot of them have in common is the idea of user adjustable parameters. And so that's on the right, all these knobs and selectors. These are all parameters that allow a musician to shape the sound of their instrument. And so then there's an idea of a patch, which is how can you save the state of every parameter at a given moment in order to either share, in order to recall the certain sound of your instrument. And so that's what a patch allows you to do. And so then I asked the question, can a VAE be used to generate synthesizer patches, which we found was a resounding yes. And so I'll talk a little bit now about how that's done. We trained a VAE, which was written in PyTorch. We trained it over 500 epochs, and we observed, much like other ML models, that your loss initially will drop quite rapidly as it starts to learn a structure, but then tapers off and sort of learns more slowly as we go. One interesting attribute about the VAE we trained here is that we're actually using a two-dimensional space, which is a very low dimensional space. There's issues in terms of lossiness because of how much data you have to encode. These are all things we were aware of, but chose to explore what a two-dimensional space was so that we could easily visualize the latent space, much like the MNIST digits. And so what you see here on the bottom of your screen is sampling from the latent space. As the model's training, we can see some structure emerge as we go. And so we found this to be interesting, but also not just seen across one parameter, but sort of all the parameters that we're trying to learn for the synthesizer. And so from that, what we did is after we had trained a VAE using a two-dimensional latent space, we tried to derive latent representations, which is what we call it. And then, like I mentioned, high dimensional latent spaces, such as the 100-dimensional GAN we talked about earlier, can often be difficult to effectively interpret, explore, and navigate. So the reason, like I said, we used a low-dimensional space was hoping to see if we could enable direct and precise control over the sampling of the latent vectors. And so then these two-dimensional latent spaces, we've generated some representations called latent coordinates and temporal representation. And so for latent coordinates, every patch in our data set that we passed or we used to train the VAE, we then pass back to the encoder network. That encoder network spits out a two-dimensional latent vector, which we then project back into a two-dimensional space. And so that's what you see in the latent coordinates. And then in temporal representation, what we do is we sample the 2D latent space in a 50 by 50 grid. And then for each section or each sampling of that grid, we reconstruct a patch using the decoder. We feed that patch into the synthesizer, record an audio clip, and then analyze that audio clip in terms of timbre, which we won't talk a lot about timbre today, but really what it is, it's an idea of what the sound sounds like. It's a commonly used thing in music, and so what we're trying to do is engage musical experts by allowing a timbral representation in that latent space. And so that's what you see on the bottom right of the page here. And so you may be wondering, why is this useful, or why is it interesting? And so I've proposed this to be an interesting, the latent representations to be an interesting way of using synthesizers in terms of a creativity support tool, as a different way of thinking about synth patches, because oftentimes the inner workings of synthesizers are complex. Small changes might result in large perceptual changes, whereas lots of changes, sometimes you never know what exactly is going on in the synthesizer. Of course, one of the main things is dimensionality reduction. And so lots of synthesizers have tens, if not hundreds of parameters. And so if we can reduce that down into a two-dimensional space, then obviously maybe for a novice synthesizer user or someone that wants to quickly explore the different sonic options, having something with a much smaller dimensionality would be super useful. And then finally, one other goal of this work is trying to escape the quote-unquote text prompt aesthetic of generative AI. I'm by no means suggesting that there's anything wrong with the text prompt aesthetic, but rather I would like to see, sort of in these creative contexts, perhaps some alternative ways of interacting with the systems and being able to have more performance-oriented ways of sampling from these generative systems rather than just asking for sounds via a text prompt. So these are all the goals of this project. It's an ongoing project with lots more work to be done, but hopefully interesting for those in attendance. So moving on, I also wanted to talk a little bit about some potential generative approaches in ocean applications that I've seen. These all come, this isn't, like I said, my direct area of expertise, although I'm interested. So these are all some resources I've scoured the internet for to see what people are working on. And so one thing that a lot of issues that have come up with training classifiers is, of course, as we know, we need lots and lots of data. And what happens if we don't have a large data set of quality data for tasks like marine plastics and trying to identify marine plastics? And so Tata proposed the use of a GAN for generating synthetic data. And that means how can we use real images like you see on the left and then generate very realistic, similar images like these ones on the right using a GAN in order to then take all of this data together and train a classifier for our understanding where marine plastic debris is in the ocean. Moving on, like I said, a quick search through Google Scholar also identified some other active research areas, which I thought was interesting, but I won't get into the details, but I will link. One was I saw using a VAE for infilling missing maritime sensor data. And so what this was doing is, say you have sensor data on, say, a ship, but then you lose some of your information, but you know perhaps on either end of where you've lost the information. If you were to train a VAE on lots of sensor data and then put your two endpoints into your latent space, you could then interpolate through that latent space in order to infill that missing data. And so that's a really interesting approach to using latent spaces in these generative models. Similarly, I saw another interesting work where they were using a VAE to forecast ocean ice concentration. So this one looked like another interesting application, trying to generate sort of further down the line. And so often this is a task I've seen done with more of a time series approach, but it was interesting to see VAE used in this application as well. And then finally, I saw another one, which was identifying sea turtle trajectories using recurrent autoencoders. And so that's a little different than a variational autoencoder, and not my area of expertise, but I thought it was another interesting way of interacting with some more ocean-related data. And so as we can see, there's lots of opportunities to apply these generative models, whether it's GANs, VAEs, or otherwise, to our own areas of interest, right? And so lots of work emerging, whether that be on explainable AI, whether that be on interpretable, latent dimensionalities, etc. There's lots of interesting stuff going on, so I would encourage you to take a look at what's out there. So a quick summary, and then we'll move on to questions, which is latent spaces are a core component of many generative systems. We talked about a few today, and we talked about some applications. Latent spaces enable dimensionality reductions. They can be interpolated through meaningfully, and they can also be used to derive alternative representations of data, such as I showed in the synthesizer patch example. And like I was just talking about, there's a wide range of applications for this type of technology in the ocean sector and beyond. And so I would certainly be interested to hear from folks how you think you could apply it to your own projects. So I'm happy to stay in touch, whether that be through my personal channels here on the left, or do get in touch with our lab, the GEM lab. If you have any questions about our active research, we'd be more than happy to chat. Here are the references for the presentation, and now we can move on to some question and discussion. Thank you very much.
Thank you so much. So it looks like we've got a question in the chat from Amy. What are some cases where VAEs are preferred to GAN or other techniques?
Sure, that's a great question, and I've wondered this as well, both in my own research and sort of more broadly. The reason I chose to use a VAE and why it was preferred to GANs is actually because the training stability we found to be much more difficult with GANs, whereas the VAE, where we know the real data and we know what the reconstructed data should be, we found the training stability in the actual ML implementation to be a little bit easier, which is why we decided to go with VAEs. But then sort of more generally, I think there will always be use cases that will be specific to your task and your domain. Like I said, there are lots of different variants of both VAEs and GANs based on what people need. But choosing the right one for your project, of course, is a key part of any ML project. And so I hope that answers your question.
Thank you. We've got another question from Alex. How does using a synth plugin using VAEs differ from synths with less knobs, which do more in the back end and are more intuitive for beginners? How does interacting with the synths you are working with on different, or how does interacting with the synths that you're working on differ from your average software synth?
Yeah, that's a great question. So I think, like I mentioned, and I only briefly touched on it, there are so many different types of synthesizers. There's different synthesizer paradigms, things like, and I won't get into too technical, but different ways of modeling sound, whether that's physical modeling, whether that's sort of more subtractive synthesis paradigms that have been classic through the last number of decades. I think the thing that's different between a VAE-based system for dimensionality reduction or latent representation versus a synth with less knobs, which is doing some more sort of back-end hidden work, is really that a VAE system, at least how we've implemented it, still gives you as much of the different sound options in your synth, while still fully acknowledging that one workflow that we encourage would be get close to the sound you want using our VAE and then adjust accordingly with a different traditional system. We're certainly not proposing that this is a perfect replacement, but rather just an alternative or a complementary tool. And then I think the second half of that question, which was about how does interacting with synths you're working on differ from your average software synth? Unless I've interpreted the question wrong, I don't think it differs at all, actually. I think we're using common or open source software synthesizers. You'd be able to go and download the exact same one and try it for yourself. And so I think it's just sort of, like I said, a different representation, a different way of thinking about using already in production synthesizers. So I hope that answers your question, Alex.
Cool, thank you. We've got one from Cooper. On the topic of alternatives to text prompts, have you experimented with multimodal inputs? For example, take a photo of a room and generate ambient music to fit.
Yeah, that's a really interesting question. The simple answer is we've experimented, but nothing to the stage of sort of where this other work that I presented today is. I think it's a great idea. Obviously, with multimodal ML, there's a lot of engineering tasks that go along with this. You need to sort of classify, if we're running with this example, you need to classify what is in the room or what type of ambient music would fit with that room. And so there's lots of data labeling tasks. There's lots of data preparation tasks, finding data sets, generating data sets, etc. One thing we've struggled with in this research is how do you get enough data for a synthesizer without just generating it yourself, which we feared would induce lots of bias, because if I'm simply generating lots of patches, they're all probably going to sound not that different from one another just because I'm good at creating one or two types, but not exploring the whole synthesizer. So multimodal stuff is certainly something we'd like to work on more. And so if you have any ideas about that, I'd love to chat more. That'd be great.
Awesome, thanks. And we've got one from Amit. Can latent representations be used for data or file compression?
Yeah, I think so. I think in the synthesizer case, we've shown actually that a latent representation does work at doing some sort of data compression. And like I said, latent spaces really are all about data compression to begin with. In this case, though, it's actually data at the parameter level rather than like at a text file level or something like that. But again, it would all really depend on your use case and coming up with a good pipeline for your type of data or your type of files. But I do think so. I think we could explore generalizing that idea to things beyond synthesizers and music.
Awesome. And then one from Amos. So can I understand the latent space just as a feature extraction vector embedding space? If so, I guess my question is, how do you find an accurate latent space that things are at what it should be at?
Yeah, that's a good question. I personally I wouldn't suggest, simply because although I think a lot about these latent spaces, I'm certainly not the world's leading expert on exactly what they are, whether it's just a feature extraction vector embedding space, or if there's more to it, or if there's less to it. But I think in general, the concept you've sort of verbalized, I think, is valid. But then your question, which is how do we find an accurate latent space with things that are where it should be? That's a great question. It's a two-part question, really, because the first question is, what does it mean for things to be where they should be, right? In our case of synthesizers, maybe that means certain sounds that sound similar in terms of how fast you hear them rather than how slowly the sound builds up. Maybe that's what it means to be the same, or maybe it really means do all sounds that sound like a bell belong together, whereas all sounds that sound like maybe gurgly noise sound similar and are placed together. So I think, like I mentioned, there's lots of techniques being explored right now for what they call regularization of the latent space, which is how do you arrange the latent space? And it'll, again, be very much domain specific and context specific. So lots of work to be done there for us in our synthesizer project. I mentioned very quickly timbre. Timbre is one thing that musicians use plenty to describe properties of sound. And so we've thought about how can we arrange the latent space based on timbre? And so that's one thing we'll look at as well. So that's a bit of a long answer to your question, but I think it's a valid way you've phrased it for sure.
Cool. I have a question that kind of stems off of that. Are there any other musical characteristics like timbre that you have considered when like arranging latent spaces?
Yeah, so timbre's certainly been the big one because, and this will actually link into, I'm reading Amy's second question as well, but we'll get to that. That timbre is a great way of describing sound from like a human language perspective rather than a perceptual perspective. But there's lots of other attributes in the synthesizer world, in the musical world, things like, for example, a filter. There's different types of filters in synthesizer, which is sort of filtering out the sound, the high frequency, the low frequency. And so maybe you want to arrange based on the types of actual modules or components of your synthesizer. There's also other things we've thought about, like how you're performing with the synthesizer. So for instance, if you're playing songs or playing music that really requires long evolving sounds, sort of like a pad in synthesizer world, maybe you want to arrange those all in one space, whereas maybe something more like a traditional piano sound should all go somewhere else. And so these are active questions I'm working on right now, but certainly a good question for sure.
Okay, cool. And Amy's question, when you
Yeah.
use days to generate synthetic data, how do you evaluate the quality of synthetic data? Hopefully not just visual inspection.
Yeah, you're totally right. Definitely, hopefully not just visual inspection. We mentioned this quite a bit in the paper that we published about the project. The way we do it for this specific project, because it's sound, is we use this timbral analysis, which spits out different timbral qualities, which is things like brightness, roughness, etc. And what we do is we take the real data and we analyze that for timbre, sort of get a good timbral analysis on the real data. And then we feed it through the trained VAE. We get the reconstructed data. We also run timbral analysis on those audio clips and then compare the loss or the error between those clips. And so we found it to do okay, not perfect, but okay. Which we certainly attribute to the fact that using a two-dimensional latent space is going to induce some loss there. But then, like you said, we try to use all sorts of metrics rather than just looking at the patches. But the best one for sure is sort of perceptually hearing it. If it's for an HCI perspective, and sorry, this is a bit of a longer answer. From an HCI perspective, what really matters isn't how perfect of an ML model we have, but rather can musicians get out of it what they're looking to get out of it. And so if it sounds good to musicians, then we consider that a success. And so some of our future work is actually evaluating with musicians through user studies to evaluate the quality of these sounds. So sorry for the long answer, but I hope that answers Amy's question.
No, that's super interesting. And Alex has one last question. Do you write or do you play music? And or are you approaching this from purely an academic lens?
Yeah, that's a great question. The answer is yes, I do. I play music. I write snippets of music. We'll wait now to say that I write songs, not yet. But I've been playing music sort of as a hobby for most of my life. Plug my SoundCloud. Yeah, I don't have a SoundCloud yet, but when I do, I'll certainly let you know. But it's been a fascinating topic to come at from both an academic lens as well as from someone who's interested in creative tasks, because there's lots of thoughts about things like aesthetic. How does it feel to perform with these creative or generative tools? But then also from an ML or an academic machine learning standpoint, how good can we make these models? And there's lots of great work being done. So in the future, though, we're going to try and start evaluating with some more musicians. So if anyone in attendance is a musician or is interested, we'd love to chat more.
Awesome, thanks. I don't see any more questions in the chat. This is your last chance to ask a question if you have a burning question. Oh, we've got a comment from Amos. If you're taking feedback from musicians, have you thought about making it towards a reinforcement learning?
It's a great question. I'm definitely not an RL expert. I, in fact, wouldn't even consider myself in reinforcement learning anything. It's not my area of expertise. Certainly, though, knowing a little bit about it, I do. I think it would be an interesting approach, but we'd have to sort of take a step back and see if we can mold the data we have or mold the task we're trying to do and see if it actually is a relevant RL task. But that's something for sure, a future work, or maybe if you have ideas about Amos, you can propose some to us, and maybe we can see if there's a good collaboration there. So the simple answer is no, not yet, but it would be interesting for sure.
Okay, any last questions or comments? You can drop them in the chat or in the Q&A box. I don't see anything, so with that, I think we're gonna wrap up. Thank you so much for joining us today, Matt. It's so great to learn more about latent spaces and that intersection between kind of a very creative space compared to a highly technical space. So I'm going to drop some links in the chat right now. The link for our student pool is there, and the link for our mentorship program, STEM Connector, is also there. So that program is a Flash mentorship program. So if you're interested in connecting with folks working in the ocean sector or connecting with other students like yourself, sign up today, and it's all free. It's Flash mentorship, so it's pretty low commitment, and you can connect with lots of different mentors. And if you enjoyed today's session, we have lots of other discovery sessions available on our YouTube channel. So I've also dropped a link to our discovery session YouTube playlist and all of our DeepSense social medias. And we've got another discovery session next Tuesday, actually, with Dr. Liu Yang about cloud. And Matt, if you've got any last words before we wrap up, now's a great chance to share.
Sure. Yeah, no, I'll just say thanks to everyone that came. Thanks for the great questions. The best part about research is certainly sharing it with the community. And so I appreciate everyone coming to chat, and hopefully we can do this again and chat more. So thanks for having me. Really appreciate it.
Yes, thanks again. Enjoy the rest of your day, everyone.